Okay, so here we're going to discuss vectors in a plane. So let's define, first of all, what is a vector. All right, so a vector is object geometrically that has a magnitude. So think of length when I mean magnitude and a direction. So that's those two quantities are what define a vector. All right, and notation-wise, we are going to use this vector with an arrow on top, and then your textbook and just textbooks in general, they'll usually use boldface to define a vector. Here, just on my screen, I'll be sticking with the arrow above the letter to signify a vector. Okay, so here, think of a vector just living in a plane, right? Not in relation to the XY plane, but just in general in a plane, right? A vector would look like this, right? Where we have here the starting point, right? And then start, and then here where the arrow tip is, they can think of that as our terminal point. So you can think of a vector u, and then a vector v. Okay, and we can also think here of also vector u and v, just a different example here. Let's say we call this vector u, and then this vector v. All right. Now, if you see in both of these examples, right, the first example here where we have this vector u, this vector v, we can see that they look like they're pointing in the same direction, but they don't have the same magnitude, right? The length is different. And in this example here, they look like they're the same magnitude, right? The same length, but they're pointed in different directions, right? So when we think of, so we have these vectors and we want to kind of build on this concept. We want to be able to compare them, right? Describe them, eventually do operations with them, right? The first step is, so we have a definition of what a vector is, and now we want to define what does it mean for one vector to be equal to another vector, right? So we want to make sure that we have a proper definition for this statement, right? The vector u equals the vector w, right? So, right, and again, this is a much different context here than if we have the statement 1 equals 1, right? Or x equals 1, right? We're used to seeing these types of equations when we're relating numbers, right? But now the equals sign in this statement, right? Just notice that it takes a different meaning, right? It's not saying that a number is equal to another number or a variable is equal to a specific number, right? So we want to define, essentially redefine the equal sign in the contents of vectors, right? So we want to say here that we want to define, right, equivalent vectors have the same magnitude and the same direction. Magnitude and direction. Okay, so in order for that statement to be true, not only do they have to be pointed in the same direction, right? They also have to have the same magnitude, right? So here, this was u, and this was w, right? Then those vectors we can consider to be equivalent, right? Same magnitude, same direction, right? Again, here, initial point, terminal point, okay? All right, this will not be true here. Like, let's say, for instance, here, u, w, right? Even though they have the same magnitude, that direction is in the opposite manner. So here, u does not equal to vector w. Here, u does equal to w, right? So both of those qualities have to be true. Same magnitude and the same direction. All right, now we want to transition here where we think of vectors not necessarily just living in some kind of plane, but in context with our xy plane. All right, so here if we had our xy plane, right, and let's say we have a point P all right, so P will define here as the point 2, 1, or excuse me, 1, 2. Let's try that again here. So here we go. We'll define that point as 2, 1, and then another point Q out here as 6, 4. Okay. All right, and then we can define a vector in this manner, right, where we have our initial point is at P, and then our terminal point is at Q, right? Whereas when we were just referring to the vectors U and V and W, we use lowercase letters here. When we define them in terms of points, it's this kind of standard notation is we have capital letters to define the points P and Q. Now to define the vector, an alternate notation is to use the points, P to Q, right? So again, the P, the first point there tells you the initial point, and then the second point here tells you the terminal point, right? So this would be different, right? PQ, this is different than QP, right? That would define a different vector that has an initial point of Q and a terminal point of P. Same magnitude, but the opposite direction. Okay, so just keep that in mind here when we talk about vectors, right? It's defined by two separate quantities. Okay, so now we have a definition of a vector. We define what it is to have an equivalent vector. So now we want to develop ways to combine vectors. All right, so let's see, how can I combine vectors? Okay, so think of these operations, right? We combine two numbers, right? 2 plus 3 equals 5, right? Or we can think of 2 times 3, that equals to 6. So we want to define two operations with vectors. One being what's called scalar multiplication, where we're going to have something like this kind of notation. And this value k is just some real number, right? Element of the real numbers. And we want to define something like this. We want to take two vectors, u and v, and we want to add them. Again, right? Here when we see these plus signs, this means adding two numbers here. This addition here is, we're redefining it essentially to mean something else when we're talking about vectors. Okay? All right, so here, let's start with the first one, this scalar multiplication. All right. So here, scalar multiplication, or this quantity here, k times v, where again, k is an element. That's what this little e means, element of the real numbers. All right. So scalar multiplication is simply another vector. So when we take a scalar and multiply by a vector, the result is another vector. So it's another vector with magnitude absolute value of k times magnitude of v. Okay, so depending on what that value of k is, it will either make it longer or shorter, right? In terms of its magnitude, right? The absolute value. Now, if it's k is bigger than 0, then it's in the same direction as v. If k is less than 0, then v is in the opposite direction. All right. So here, for example, if this was a vector v, right, 2v would look something like that. And then like half v would look something like this. And negative 1v, or this is equivalent as saying negative v. That would be something like that. Okay. All right, so that is how we're going to define scalar multiplication, geometrically at least. When we talk about components in terms of our xy plane, we'll take a look at what that looks like in our xy plane. But for now, that's what we have. So now, our next operation is adding. How do we add two vectors, right? Okay. So here we can think of there's two different ways to calculate the addition of two vectors. One is to take the terminal, or excuse me, the initial points of u and v. So let's say we had, this was u, and then v was over here. And we want to say, well, what is the resulting vector of adding u and v? And so one thing we can do is we can think of, let's place the initial point and then have the vectors go in their own directions, right? Wherever u goes and wherever v goes, right? This is called the parallelogram method, and we go to the initial or the terminal point of u and draw a parallel line to v, and then go to the terminal point of v and draw a parallel line to u. All right, and here where they meet, these parallel lines, that would be the terminal point of my resulting vector u plus v. Okay, so that's the parallelogram method. Another method would be the tip to tail method here. So here, what we can do is we can say, all right, so we can start off with our vector u, initial point, then the terminal point, and now at the terminal point of u, I will put the tip of v and then draw it out there. All right, and now at the terminal point of v, I'll reach out from my initial point of u and go there, connect them, and that becomes my vector u plus v. Okay. All right. So that's the tip to tail method and the parallelogram method, equivalent methods to find the addition of two vectors. Now another operation that we'll define is subtracting them, although we can really think of subtraction, right? There really is one operation, right? Addition. We can think of subtraction as just the addition of the negative, the additive inverse, or just a negative value of, in this case, u. Okay. All right. Here, and one way to think of this okay, so one way to think of this here, v minus u, right? We can put them at tip, both at the same initial point here. This is my u here, and then my v. Here, instead of doing the parallelogram, I use the, this is v, this is u here, going whichever one I'm subtracting, going from the terminal point to the terminal point of v. This would be u minus v. Right? And an alternate way to think of this is also here, similar to the tip to tail, where we'll have v here, and then u goes in the opposite direction there, and then our resulting vector here, this would be u minus v. Okay, so geometrically we can think of the subtraction of these two vectors in this way. Right, now in our next video we'll take a look at, well, let's focus on the components, right? Algebraically, these will be living in the xy plane. So how can I use those quantities to have an algebraic way of combining vectors?